Welcome to the lectures on modern digital communication techniques. We are continuing our discussion on digital modulation methods. In the previous lecture, we have given an introduction to digital modulations, where we have identified the fundamental essence of digital modulation, and we have used the terminology symbol mapping, which we have described in qualitative terms what is meant by symbol mapping. So, we will continue further to take a look at a few modulation methods in this and subsequent lectures. So, when we consider digital modulation, as we have been doing, so it can be classified in various ways. So, one of the ways would be memoryless modulation, and naturally the other counterpart would be with memory, right. So, when we say memoryless, what we mean is that suppose I have a sequence of zeros and ones, right. A memoryless modulation would map this particular 0, let us say, to a waveform which is here, and then let us say a 1 to a waveform which is here, and then a 0 again, right, to this one, and again a 1 to, let us say, right, this one. And what we mean is that when it maps these symbols to these waveforms, it only looks at the current symbol and maps to the waveform. It looks at the current waveform, maps to it, looks at the current symbol, maps to this current symbol, maps to that. It does not look at anything more. It does not look at what was the past modulation and what could be potentially the future symbol that would be sending into. Whereas, with memory modulations, we clearly look at the previous and the future bits that are going to come, or the symbols that are going to come. So, it is basically looking at the previous output, that what was the previous output. So, there is some kind of memory involved in the past. Memory means it is the past, right. So, when we say with memory, it uses some information of the past in taking action on the present. So, that is a basic way of classification, and you could also classify further as linear modulations and naturally nonlinear modulation. So, when we say linear modulation, what we effectively mean is the principle of superposition holds, and here it does not hold. That is as simple as that. So, what it effectively means is that if I have two inputs, then the output could be expressed as a superposition of the outputs of two different inputs. So, in that case it will be linear modulations. We will be mostly dealing with linear modulations. A brief note on with memory. If you look at transmissions which use memory, so one particular example could be the trellis coded modulation, where there is a particular way of traveling a particular graph, and there involves some kind of memory. And these kind of modulation techniques are generally very robust techniques, and they are used for to encounter certain kind of errors which the symbols might have in the channel. So, they usually have an inbuilt error protection mechanism into these into their transmission procedure. However, most of the common modulation techniques that you would encounter, let us say in everyday life in commercial systems mostly, you would find that the modulations used mostly these days are memoryless modulations, and these error correction codes are usually handled through special techniques known as forward error correction codes. So, there is a whole lot of theory on forward error correction codes, and one would use encrypted or encoded bits. These bits are then passed on to a particular to the modulator, which is memoryless, and the modulator's job would be to send the signal across the channel, and the error correction code's job would be to protect the bits from getting into errors, right. So, generally we would talk about memoryless, and generally we will also talk about linear modulations, but we would also spend some time on nonlinear modulation at an appropriate point of time, right. So, with that brief classification between memoryless and with memory modulations, or let us say linear as well as nonlinear modulations, it's important, or it's time now that we get into one of the earliest, one of the first modulation techniques. And one of the first modulation techniques in the class of memoryless modulations, which we will begin with. So, we will begin with memoryless modulation, and the first signal or the first modulation technique that we are going to look at is pulse amplitude modulation, right. So, when we talk about pulse amplitude modulation, in short, you will usually encounter this name PAM, right, pulse amplitude modulation. So, what it does, it basically maps these inputs to waveforms which differ from each other in terms of amplitude, right. This is what we mean by pulse amplitude modulation. So, a pulse amplitude modulated signal Sm of t, we could write it as Sm of t is usually represented as the real part of Am, right, M indicating message or modulated. So, this is Am is the amplitude, there is Gt, and there is e to the power of j 2 pi fct, right. So, at this point you may recall amplitude modulation, which you have studied before. Amplitude modulation, you would have 1 plus k amplitude modulation coefficient times mt times cos 2 pi fct, plus of course there is some theta associated with that. And if you look at this, it will be real part of Am. So, if Am takes real values, it will be Am, and Gt would be again taking real values, which is indicating the pulse. So, basically what we have is G of t is a real valued signal, right. So, Am is the amplitude, and where M takes on values 1, 2, 3, capital M, and this is valid, this particular notation is valid for time less than equal to capital T, which is greater than or equal to 0, right. So, we will shortly explain what is this. So, with this particular representation, what you get over here is Am Gt cos 2 pi fct. So, this is not much different from amplitude modulation if I remove this A1, which is basically the suppressed carrier. So, this is a suppressed carrier double sideband amplitude modulation that you get. The difference with amplitude modulation that you have over here is you have amplitudes with certain possibilities, right. So, you are selecting one particular amplitude, and this amplitude selected is further shaped by a waveform, which is known as the pulse shape. This is one of the very important things of digital communications. So, with the pulse shape, and this signal is valid for a duration between 0 to capital T, and since you are selecting the amplitude, pulse with an amplitude. By pulse we mean some duration of time. This is a rectangular pulse. You could have pulse which looks like this. So, pulse, and you are selecting an amplitude for it. So, that means you could have a pulse with this amplitude, or you could have a pulse with this amplitude, or you may have pulse with this amplitude. And there is a carrier. So, when you are modulating that, your signal would appear like this, or if you are modulating this here, your signal would appear in this form, and so on and so forth, right. So, there is an amplitude, there is a pulse, and you are modulating the amplitude of the pulse. So, that is why pulse amplitude modulation. And because you are modulating, that means you are changing the amplitude of a carrier, therefore, you are calling it the modulation, right. So, there is a lot of similarity with analog communication, except that you have the waveforms to select which are discrete in number of options, but the waveforms themselves are analog. So, if it is a rectangular, which is easier to visualize, let us take one and let us take another. So, these both are valid for the duration 0 to t. So, in the first case, the modulated, this is S1 of t, and this is S2 of t that we get. So, you have two choices, S1 and S2. So, if you get a 0, you might choose S1. If you get a 1, you get S2. So, these zeros and ones are the sequence of zeros and ones that keep coming, and this choice would be valid for this duration t, right. Now, some interesting things come in. So, instead of just having two options, if I would have, let us say, more options. So, as we just discussed earlier, if there are k bits, so that means we are grouping k bits. So, in this particular picture it represents 3 bits. So, we should have 2 to the power of 3 waveforms, because whenever you select 3, you are going to get 0 0 0, 0 0 1 dot dot and so on up to 1 1 1, which are basically 8 waveforms, right. Sorry, 8 possible combinations. Each combination should map to a waveform. This means I should have 8 different amplitudes. This is not dependent on m as per this representation, only the amplitude is dependent on m. So, now these things come at an interval. Let us say we define T b as the duration of the bit, right, duration of the bit as T b. So, if this has a duration of T b, then you have to wait for k bits, you have to wait for k bits, that means in this case 3 bits, before you get your group of 3, before you can form this particular symbol. So, once you have waited for this 3 bits in this example, or k bits, and you have formed this k bit word or this k bit symbol, now you can select a particular waveform. So, you get a bit, you wait, you get the second bit, you wait, and then till the end of the third bit you wait. So, in this interval, now you have formed a word consisting of 3 bits, right. Now, the next word will again take this much duration of time. So, what the transmitter does, it sends this particular waveform, whatever is the waveform, for a duration of time which is basically T s, which is known as the symbol duration, which is same as this T. So, therefore, what we are doing is T or T s, as you may call, is equal to k times T b, because now each of these waveforms should accommodate 3 bits. Now, why did we have such a relationship? And of course, at some point you can say that if you have r bits per second, that would definitely mean that 1 upon r is equal to TB, that is what we are using, is seconds per bit, right. So, why do we need this? We need this for the reason, because if we are taking the modulator at some point in the transmitter, we know that bits are coming into it, and we know the modulator should choose a waveform, or let us say a waveform like this, right. Let us take 4 options. Or let us say even a bigger one. So, these are the 4 options. So, this is S1 of t, S2 of t, S3 of t, S4 of t. So, if it has to choose between these 4, so that means it will be grouping 2 bits at a time, right. So, now if this was sent across one bit duration, that means I could send it in this short duration. If I would send it in this short duration, then in the next bit interval I would be sending nothing. So, that means I would wait to form this group, but in this interval I would send away my waveform. So, I could send it away in this waveform, I could send away like this, and then in the next bit duration I would not send anything. I would not send anything, whatever had been my choice there. Again the next one I could choose this, depending upon my sequence, whatever it is, right, and again I would be sending nothing, right. This is a bit awkward from multiple points of view, and one particular modulation scheme could be that the first waveform has an amplitude of 0 and the second waveform has an amplitude of something which is non-zero, which is also known as on-off keying, which is a special case of what we are dealing over here. So, in that case, when you are not sending anything, that could account for certain information being sent. So, generally we would not do a situation like this. Neither we are entitled to send this waveform which is longer than the duration of k bits, because if you were to do that, that means if you were to take a duration which is more than k multiplied by TB duration, then when you have a whole stream of bits coming in for a very long duration, the modulator would have to create a huge buffer, and then the rate of things going out from the modulator would be at a slower rate than things coming into the modulator, and it would act like a sink, right. Now, if the modulator sends things at a rate which is faster than the rate at which things come in, that means it would be generating waveforms even if there are no bit streams, which would act like a source, which is again an undesired property. So, we would like the modulator to work in a way where the rate at which bits come in is the same rate at which effective number of bits go out. So, what we see over here, in this duration t, there are k bits that go out. So, that means in k bits take t duration to go out. So, definitely one bit would take t upon k, and one bit would take t upon k, and that is TB, and that is exactly what you have over here. So, what we effectively mean is that if there are k bits, right, in that case your symbol t should be equal to k times TB. That means, this duration, pulse duration, should be equals to k times TB. So, this is also known as the symbol duration, and these are your symbols, these are your effective symbols. So, these are some of the essential things that we should remember whenever we are studying a modulation process. Now, we can move further with our discussion on amplitude modulation, and we can say that these AM amplitude values that you are taking is valid for m is equal to 1, 2 up to let us say capital M. This is for notation, and you could design AM as 2m minus 1 minus m times d, wherein 2d is the distance between adjacent amplitude levels, right. So, what we mean by this is one particular way of mapping to amplitudes, right. This is not an hard and fast rule that you must follow, but this is one standard policy or methodology by which you could select amplitudes. So, for example, I have m is equal to 2. So, your small m can take a value of 1 and 2, and AM would be 2 minus 1, that is 1, minus 2, right, that is minus 1. So, that is minus d, and when m equals to 2, it is 4 minus 1, that is 3, minus 2, it is 1, it is d. So, what we are saying, in one case you have S1 of t, which is equal to minus d times gt cos 2 pi f c t, and S2 of t equals to d times gt cos 2 pi f c t, right. And of course, all of these are valid for the duration of time which is indicated by this, and where of course t is equal to k times Tb, right. So, effectively what we see over here, we still have this unknown parameter d, right. So, if we would look at this diagram or this particular amplitude levels, we could draw a picture indicating this amplitude levels. If this is 0 and this is plus d, this is minus d, we could say this is S1, this is S2, right. So, that means the amplitude, or this is A1 and this is A2, this is the amplitude of the first symbol, this is the amplitude of the second symbol, and these are carried through, right. And what is d? So, by choosing a value of d, you could make these amplitudes smaller or larger. That means, for a certain value of d, my waveform could be this, and the second waveform could be right. A different value of d could have my first waveform as this, and my second waveform could be same as this, does not matter, or could be even smaller. So, what I effectively mean is that this distance between the two is governed by d. So, if I make d equals to 1, then this value is 1 minus 1, and if I make d equals to 2, in that case this will be 2 and minus 2. So, when it is 2 and minus 2, what we see that the distance between this is much more than the distance between these, and what will be clear, this situation will require more energy, but it will be more resilient to noise than this. So, effectively what we have is, by suitable choice of d, you could effectively have different waveforms, right. And in this particular case, what we have is these are simply distinct by virtue of the phase, which is d and minus d. So, here what you could say is that you are basically having a waveform like this, and you are basically having a waveform of this, right. And of course, you have a bigger d equals to 1 in this case, d equals to 2 in this case, you could say. So, one is so there is a much more energy in this case, there is much lesser energy in this case, and this will be more resilient to noise than this particular case, right. Okay. So, how these things matter we can see even a bit further down. A further important concept here would like to bring into is the notion of carrierless modulation. So, if we let f c equals to 0, that means in this particular, if we let f c equals to 0, we are left with a m g t. So, if you look at a m g t, in this case we would be able to, we can use almost this particular thing. The picture that we have here is, we would say that suppose I have a 0 and a 1 sequence. A 0 would mean I have an amplitude of plus d for the duration of t, and a 1, let us say, would mean I have an amplitude of minus d for a duration of t, right. And then if there is another one, I have an amplitude of minus d. So, if this is 0, this is d, this is minus d. So, I have got 0 1 1 to send, 0 1 1, I am mapping 0 to plus d, 1 to minus d. This is what I am going to send. Now, if I have a carrier, my things will not look much different, except that there is a carrier, right, and then there is a phase reversal. However, here there is continuity of phase because we are not changing, right. So, what we see over here is that in case of baseband, so this is typically you would call baseband pulse amplitude modulation, and this would be the passband pulse amplitude modulation. So, this modulator that we had discussed earlier, here we could still analyze our system without up conversion, and we would be able to analyze the system in our low pass equivalent form of what we have studied before. So, what we see is that we have now come to the point where we would be using whatever we have studied our previous in our previous lectures, that is the band pass signal and its low pass equivalent representation. So, if you would recall, the low pass equivalent representation is the translated signal from f c down to 0, that means which is carrierless. We will be using a similar form throughout the study, and I have given you just now a representation of how things would be for a typical carrier. So, we will continue on this in the next lecture, where we will look at the diagrammatic representation for a 4-level pulse amplitude modulation, and the few relationships pertaining to pulse amplitude modulation. Then we will move on to phase shift keying, and finally covering quadrature amplitude modulation before moving on to a few more other modulation techniques. Thank you.